Welcome back, and let me continue the presentation related to the properties of the local Brouwer degree. This lecture will concentrate on the properties related to the composition formula of the degree. So let me simply start writing, and let's write it down. This will be a theorem. And let me write it, the title, so this is composition formula for local degree. And let's continue. Assume that the dimension of the Euclidean space which we are considering is larger or equal to 2, and let omega contained in V be a non-empty bounded open set point. In addition, suppose that we have here two maps. So, of course, here you will notice that I'm not considering the map to be defined on the whole space, but that's just simply for the convenience of let's say, explaining this property. So, in any case, you can always remember that by T's extension formula, every continuous map defined on the closed subset, in our case in the Euclidean space, can be extended to the whole space. So that's not a problem here. And G is just a map from V to V. So suppose that R two continuous maps such that, and here we have, for every x belonging to omega, we have here G, F, and this will be x is different than 0. So that means simply that the composition G and F and omega form an admissible pair. So this is admissible pair. 10, of course, denote by, and this will be uj. I'm not specifying the components. There can be infinitely many of them, but for a moment, let's say, it's better not to write. As you will see, we will have actually the situation that it deals only with the finite number of those components. So the family of all bounded, connected, open components means connected in such a case, because it's open to the also part connected of the set V minus f, and I take the image of boundary, which is a compact set, so that definitely is a closed set, so that is an open set. So we have it, and assume that we have Pj belonging to Ej a fixed. You see? Maybe write it down. Maybe that. Just simply write that is a fixed element. So Pj that belongs to Uj are fixed elements. So, then we have the statement. We put it like this: star, the degree of G composed with F, maybe a second, composed with F on omega will be equal, and this will be equal, and this is J, and this will be degree, and this will be F minus Pj omega times degree G Uj. So Ui. No, Uj, correct. Uj. J. And we'll show also that this actually is a well-defined expression, and it makes sense to write it down, as you will see. So let's put it. Okay, put it. Okay, sorry. Proof first. Proof. And then you can write it down. Put our set U will be the set composed of all bounded components of the set V minus of this set simply. So this is the set composed of all bounded components. So this is our U. This is our U. So put it like this by definition. And let's say in such a case, by assumption, U is open and bounded. So let's say is open and bounded, and we also have here that G minus 1 of 0 intersection U closure is contained in U. So in a certain way, that means also that so we have here that this G and here we have U is admissible pair. So is this clear that this is, so let's look at the assumptions. You can see that yes, this is non-zero, so in such a case, since you can see that the boundary boundary of the set U is exactly the image of the boundary of omega, so in such a case you can easily figure it out that that means exactly what it is written here, that there cannot be solutions on the boundary of U. So let's continue. Let's continue. So put. And we put several numbers. So let's define the first number. By the definition, it will be 1/2 of infimum, and here we have here x minus y, and then you have here x belonging to the boundary of U, and then and y is belonging to the g minus 1 of 0 intersection of U, which is inside. So we claim that this number is positive, indeed, by the previous remark, and maybe also have a kind of an idea what that actually means. So if this is, for example, no, let's put it like that. If my set U looks like this, so it's composed of two components, so you have here like this U1, this is my U2, and you see here we have some zeros, so there are zeros here, maybe like this, compact set, so put it like that, compact set, and so those are zeros of G. So what we are doing here, we are finding a number, that means epsilon 1, which will be like in this case 2 epsilon, will be in this case, so let's see like this, this will be this distance, this will be 2 epsilon 1. So let me write it down. If I take this neighborhood, so here you see all zeros now. So all zeros of the function G are outside of this 2 epsilon neighborhood of the boundary. And the same here, so we have here the same here. Here the same here. And the same here. So this is 2 epsilon. So very good. So also we put here epsilon 1 is equal again 1/2, and this will be 1/2, and this will be infimum, and this is x belongs to the boundary of omega, and this will be g f of x, and that one is larger than 0 as well, and finally epsilon 3, again by the definition will be again 1/2, and this will be infimum, and this is y belongs to the boundary, and this will be g of y. Very good. So now by Weierstrass and Sard's theorems, we can find C infinity maps such that omega is going to V, so those are tilde maps, and G tilde that goes from V to V, such that we have several conditions. So let's start with A, that 0 is a regular value of G tilde composed with F tilde restricted to the omega. I can write omega bar, but basically here the next conditions will actually exclude the possibility of having zeros on the boundary, so we can use omega instead. And B, and I will just use here bullets of it. So the first condition is like this, that we have here supremum x belongs to omega, and then you have your absolute value f of x minus f tilde of x is smaller than epsilon 1, and then you have here supremum x belonging to boundary of omega, so here is only for the boundary, f of x minus g tilde of f tilde of x is smaller than epsilon 2, and finally supremum y belongs to u, and this will be g of y minus g tilde of y smaller than epsilon 3. So again, so this is epsilon 1, this is epsilon 1, epsilon 2. So how do we find this? So of course, first we can find a map, smooth map. You can choose, for example, the map that is smaller than epsilon 1, like this f tilde and g tilde epsilon 3, and so these three conditions are satisfied, so we just start with the maps f and g tilde, which are c infinity, so this will be maybe in red, to don't mix up with the text, so this will be f tilde and g tilde c infinity, so there will be smooth maps. By Weierstrass theorem you can find it. You can always choose these maps to be as small as you want, but for example, you can even take these maps, smooth maps, to be smaller than epsilon over 2 epsilon over 2 epsilon in 3 epsilon smaller. And then once you have this smooth map, you apply the Sart's theorem, because in such a case you know that the map, the map G tilde, F tilde composed with this map has the set of regular values open, so the regular values open and dense in Rn. So once you have it, so what you do, you just simply choose the regular value, which is, for example, again smaller than any of those, so you can assume that, for example, epsilon 2 divided by 2, and then you correct it, and you will be getting a map. So that means you take it and correct it minus this regular value. You will be getting a map that satisfies the condition is A. So this map satisfies the condition A, and that means we have B and A satisfied. So all these conditions in such a case would be satisfied. So that's how it is. And since we have here chosen these conditions 1, 2, and 3, so you can see immediately that the condition B, that one, this condition, implies immediately, as it is defined, that we have here, so put it like this, value, so clearly we also have the properties, that this is C, the degree of G composed with F on omega is exactly the degree of G tilde composed with F tilde on omega. So now we have reduced the problem of computing this degree of G composed with F to computations of the nice regular maps. Notice that so maybe notice that then, of course, by the regularity of that map, we have here the following. Then put it like this: 10. If I take the G tilde f tilde, and I take minus 1 of 0, and I look at the all possible zeros, but inside the omega, then I will get the set, so say like this, we have here the set x1, x2, and here we have here xn, so those will be my points. And then of course, I can take these points and I can apply the map F, and you will be getting this set, call it like this, y1, yk, this will be the image of those, so put it like this, image of those regular points. So it is easy to see immediately by the definition of the regular point that the image of F, if you take this image, y1 will be also composed of the regular points of the map G, that is clear. So let's write it down. So using the analytic definition, so put it clearly, by applying the analytic formula and the homotopy property of the degree, we obtained. So in such a case, we obtained that the degree, and this will be G tilde, and this will be F tilde, omega is equal, and here we have here J is equal 1 to M, and this will be signum determinant, and that means derivative of GF tilde, of course, at the point xj, so j1 to m. So now let's continue. So this will be equal by the let's say by the derivative of compositions of derivative. So of course that means this will be signum determinant, and then you have here d, and here we have here now let's put it f, first one, interior, xj times, and this will be signum determinant, and this will be d, and this will be g of f at the point f of j, again tilde, close it. So now that's determinant. So that's interesting thing is that actually I can write that value here basically as the value, and let me write it down, and I can write it down, I is equal 1 to k, and write it down, this will be signum. So signum determinant, so this will be degree, I put it like degree, but again by the analytic formula, this will be y1, and that will be on omega. And let me explain it. Signum determinant again, this is unchanged, and this is d g tilde, and I put here y1. So let me explain what happened in the last line. So suppose if this is our omega, so this is my boundary of omega, those are my points, and then of course this omega, so let me still write it down, that's my omega, is mapped, so it's mapped on the, and here we have the map F. So the map F, and here maybe I put here something like different color. So maybe this color. And this is the image. Oh, this is the image. This is the red points are going here. So it's kind of looks like that. So that's the image. So you can imagine so that now the points, if you this point x1, for example, this is your x1, it goes here to y1, and x2 goes to here, y2. So that means, and then of course maybe x3 goes here to y3, and x4, okay, who knows, maybe it also goes to x1, and x5 goes here. I put here like this, y0, this looks like a different point. So this case, in this is possible, so we will denote u0. u0 is the unbounded component of v minus f of omega. So let me write it down. So we have here fx1 is equal to fx4 is equal to y1, and then of course you also have here f of x2 is equal to y2, and f of x3 is equal to y3, and f of x5 is equal to y0. So that's basically the situation we have. That's basically the situation we have. And now if you look at the formula that we have here formula. So now you see you are computing this determinant. So if you look at this determinant, so you compute this determinant, and you can see that here the number of the points here, so you take that point, you see, and that so put here like this, determinant of that function, so basically means simply that, let me put it here, I will write it correctly. So that point actually you can say f tilde, maybe remove this blue color, f tilde minus y1, so this will be 0, so you can see that this is 0. So that means what we are computing, you are computing the determinant of this particular map. So in such a case, you can see that all the images, inverse images of these points here, so of y1 gives you this degree, exactly this degree. For example, for y1, this will be y1, that degree. If you change to a different point, then of course you will be getting different sum, but still it will represent this particular degree in omega. There are no other zeros for that value of this shifted form map f. So that means simply that this formula, signal determinant, if you sum up all j related to this inverse image of yi, then you will be getting exactly this particular formula that is written below. So that's it. So maybe let me continue, and so we have already the component E0, and since each point yi belongs to a component and we don't know which one, so let's simply write it. It belongs to a certain component, so put it like this, uj of y, so that means for this I there exists a component uj. It can be 0, it can be unbounded, okay? Therefore, it can be connected by a continuous path, because by a continuous path to the point, and let me write it down, P, J, I. Yes, we did it. We chose these points in the very beginning. So we chose these points here. We had these points chosen, except we didn't choose anything for U0, so, but we can do it now. We can also add this P0. So here, I put it like this. Here we choose P0 belongs to the U0, so this is unbounded component, such that P0 does not belong to the f of omega bar. Yeah, because it's unbounded, so I can take it far away as much as I want. And f omega bar is compact, so of course I can choose it far enough not to be in the image. So again, let's make a picture. A picture is again showing the situation. So here we have here, this is my image. So again, we have here, this is my U1, this is my U2, and this is my U0. So I choose, for example, my points. So here we have here P2, this one is my P1, and if the image is somewhere, so I put here like this, for example, P0 is, it's not in the image. Then of course, as we have here these points, these points U1 and U2, so for example, did I do something incorrectly? Yeah, so this is U2, so we have here Y1 standing here, so we can connect this one, Y1, by a path. There is a path, and we connect it. This is continuous path. And then you have here 2 points, and then this is there are 2 points here, like this, or 3. Okay, Y2 and Y3. So for them also exists a path. So let me connect them. There exists a path, and there exists a path connected this. So if this is something like a sigma, maybe not sigma. Yeah, maybe sigma. Sigma 1 of t, and this will be sigma 2 of t, and this will be sigma 3 of t, and it all goes to that one. So that means in this case, here we have also y5, let me check. Y0 is connected to P0, and this will be C0 of t. Then of course you can replace this function here by the homotopy. So you can replace this by homotopy. Let me point out this one. And the homotopy would look like that. So we just simply take f tilde minus, and in this case it will be sigma j, and this sigma j of t, and that's your homotopy, and this homotopy is between f tilde minus, and this will be yj, and it will connect it with f tilde to pj, sorry, I of j. No, it's not correct. I. Sorry. I use I, and then this will be T, and this will be the homotopy that gives you the connection between that one minus yi, and this will connect you to f tilde minus pj of I. Okay, pj of I. So that means in such a way in such a way we obtained an admissible put it like this, omega admissible, and omega admissible homotopy, maybe not n, just admissible homotopies. So we have by the property, by homotopy property, that degree, and let's start again. G composed with F omega is equal degree of G tilde composed with F, like we showed above, and then what we get here is now is equal, so put it here, is equal, and now we can use this homotopy property. I is equal 1 to k, this is the number of components that we are considering, and then the number of elements in the set y1, y2, yk. So this is the set of zeros in the U. So this will be degree of f tilde minus pj of I, and that will be again on omega. And here we have times signum determinant of dg tilde of of y I, and that exactly by the definition, by the analytic formula, you can simply remove it. So that means simply, let's say like this. Okay. This is exactly J. Sorry. I. Yes. No, that's J. J. Yes, this will be degree of f tilde minus p I on omega, pi on omega, times degree of g on uj. So again, this is the summation. So you can now see that these two lines are actually denoting the same. So there is no problem with the signum. So if you look at the signum here, this one. So here you are taking all possible. This is tilde, of course. You are taking all possible points of the G. So this is all in U, and then of course by additivity property you are getting that property. This is equal to the degree of on components. In this case, of course, for each such component, we are getting here the degree of the particular reduced, means this reduced by this above homotopy map f minus pj. So now again by the homotopy property we can go back and you can rewrite it down. This will be the degree of f minus pi omega pj, of course pj Pj, 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 yes, and this will be the degree of G, U, J, Pj, yes, J. I hope everything is okay. So for a given I, you take the summation of all these terms here, and then you are getting for a given component, for a given component J, you take all the summation here, and you are getting that formula, and then of course summation of J gives you the final formula. Notice that only finite number of components by the compactness of the set of zeros participate in this computation. So that is basically the end of this theorem. This is the end of the proof. So that's the end, and let's go to the next property, which will be related to the let's say to the original work of the Brouwer, original work of Brouwer, and of course, let me put it put it couple of remarks in this context. So let's say denote by pi n the set of all homotopy classes of continuous map and I put here sigma that goes from Sn to Sn, and here of course we assume that n is larger or equal to 1. So that's the set. I don't talk about let's say the group structure here. Also we know that there can be defined a group structure that's a part of the, let's say, basic homotopy theory that starts with the homotopy groups of spheres. Everybody knows that there can be introduced a structure of a group in this Pn, but for a moment we are not really concerned about it. For us it's just a set. What we can do is we can use Titze theorem by Titze extension theorem there exists an extension, a continuous extension of f of sigma to f sigma that goes from v to v. What is v? Here v is equal r, sphere is n, so this is n plus 1. So that means this one. An extension means nothing else than f sigma restricted to Sn is exactly to sigma. So notice that this extension f sigma is, put it clearly, B1, 0. So this is the unit ball in V, admissible. Therefore, we can define the number, the integer number, and denote this number degree, and I put here sigma. By the definition it will be exactly local degree that we just introduced. We take f sigma and apply it on B1 of 0. So this is this local degree. This is the local degree. Couple of remarks, of course. Remark. For any representatives, put it like this, sigma, maybe put it, sigma and sigma prime belonging to the, okay, to the homotopy class of certain alpha that goes from Sn to Sn. So this is a homotopy class of that map, and there are two representatives. So of course that means simply that alpha is homotopic to sigma. Alpha is homotopic to sigma prime. So that means they have the same homotopy as alpha class, and that means we have two sigmas representing this class. So in this case, one can immediately notice that by homotopy property of degree, of local degree, we have here the degree of f sigma b1 0 is actually equal to the degree of f sigma prime of b1 0. So the formula, call this formula double star. So the formula double star defines a map that is actually written like this. This is degree, which is defined on the homotopy classes of these maps, and this goes to Z. This goes to Z. And this map, so we will call and let's write it down, deg of sigma, or deg of this homotopy class of sigma. See, it's here, deg of sigma, or homotopy class, the degree of sigma. So actually this is related to the work of Brouwer. In fact, notice that it was kind of a known fact that this pi Pn, as I said, it has a structure of the group. So the statement here basically could be formulated that this degree is an isomorphism of these two groups. So this is an isomorphism. So this is an isomorphism. And that property is also known, that this is an isomorphism, as the Hopf property. So the Hopf property and I'm not going to talk about this. We won't really need this Hopf property. So the Hopf property says simply the homomorphism, the group homomorphism. It uses the fact that this is a group, the group homomorphism deg from pi n to z is an isomorphism. So that's how it is called. So okay. So we have the degree. Maybe just for the completeness of the presentation, let's write couple of basic properties of this degree. So put it like this: theorem. And we'll call it properties of deg, of this function deg that we are talking here. Maybe So start it again. Suppose n is larger or equal to 1, sigma tau from Sn to Sn are two continuous maps, then we have, and then we have A, if sigma is homotopic to a constant map, then degree of sigma is equal to 0. And B, if degree of sigma is different than 0, then it is surjective, then sigma is surjective. And C, if sigma of minus x is equal minus x is equal minus sigma of x for all x belonging to Sn, then degree of sigma is an odd integer. And finally D, degree of tau sigma is equal degree of tau, and this is times degree of sigma. Good. So that's the statement. And let us do the proof. So start with A. So notice that if H, that is defined 0, 1 times Sn to Sn is a homotopy between sigma and a constant map, then by Tietze extension theorem, it can be extended to a homotopy. And this will be written like this, homotopy capital H, and this will be 0, 1 times V to V between let's say F sigma and a non-zero constant map. Indeed. Just look how it is. Here we have the homotopy, so let's write it up. Oh, we have kind of a cylinder, because the bottom of the cylinder is S1. So this is 0, this is 1, and that in the bottom this is sigma, and it goes here to the circle, and this is a homotopy, so at the top it is actually going to constant certain value c on the circle. So this cylinder is empty. This cylinder is empty, so put it like this, empty inside. Empty inside. And then of course you can immediately see that since this is a constant map, so I can extend it on the top. You can take the whole space and you can extend the whole space here to the constant map here. So now you have a situation where you are having here 0, 1, and this is times the cylinder, so this will be like 0, 1 times Sn, union, and this will be 1 times V. So this map is given by the homotopy, an extension by constant, and it goes to V, and by this Hopf theorem, that's a closed set in the product space, so can be extended. So this can be extended to 0, 1 times V, and that's my homotopy H. So this is small homotopy and constant. Maybe put it red. Small homotopy and constant, and this is capital. So you are getting such an extension. And this implies here, this is such a homotopy exists, so this implies by the existence property, by the existence, I think it was P4, we obtain that if map has no zeros, so degree of f sigma on B1 0 is equals to 0, so that implies that the degree of sigma is equal to 0. So that's good. Okay, so now of course, in order to prove B, let us look at the place. So suppose sigma is not surjective. Sigma is not surjective. So let me see. So let's make a picture. So this is my sphere, two-dimensional sphere. So this is my S2, and this is my sigma f, and of course everything goes to the sphere. So here we have the situation that this is my sigma, and my sigma is such that it's not covers, so put it like that. The image is here, so that means Sn minus a small ball, so this is a small ball here, of a radius epsilon at certain point x naught, so this is my certain point x naught, and this one contains sigma of Sn. Because it's not surjective and the image is compact, so if the image is compact, that means there is a small ball around certain points such that this will be not belonging to the image. So that means we have here such a situation. And now it is interesting to look at the sphere with this cut off small ball. So that thing, if you homotopically. That means if you can deform, you can just simply look at that one as a subset of the space, let's say Rn, in our case Rn, so this is V is equal Rn plus 1, and then you can think about that small value here, that guy. Oh, this is the small ball that we cut off. Sorry, not here. Outside is a small ball, so maybe this one is the cam. You see, it's like a stereographic projection from that point. So this will be the boundary here, and goes here, and everything else will be this value. So now you can see that this is contractible set, this is a contractible set, and you can use a deformation here, shrink it to one point, so shrink it to a certain one point, and you can see that since you can do this shrinking operation on the sphere itself, so that implies simply that sigma in such a case is homotopic to a constant map. So one more time, you cut it off, your image is outside of this red ball here, red ball, and you shrink everything, like shrink everything. Yeah, shrink everything to one point here, like a deform, deform it to one point. So this will give you the homotopy of sigma to a constant map, and clearly you will be getting that. You will be getting that this is a constant map. So degree, by the previous statement, degree of sigma must be equal to 0. And of course, by contraposition, the statement follows. So we have here this statement proved. So now, let me prove the property C. So let's say like this, C. So the C is the direct consequence of the Borsuk theorem. They put it like this, property, this property follows from Borsuk theorem. Then degree, that means if sigma is odd, then f sigma is odd on Sn, which is the boundary of B1, 0, and degree deg of f sigma B1, 0 is an odd number, odd integer. So we got it. So now let's finish it and prove D. And so assume that we have also given two extensions. F sigma is an extension of sigma, and f tau is an extension of tau. Then, of course, since sigma of Sn is equal to, okay, maybe like this. Okay, maybe start like if sigma is not surjective, then sigma is homotopic, then sigma is homotopic to a constant map. And in the same way, look, the composition, sigma and tau, so tau and sigma like that, is also homotopic. To a constant map. And in this case, we have that degree of sigma and tau and sigma is equal to 0, and that one is equal to the degree of tau times degree of sigma, because this is also 0. Okay, so it is satisfied. So assume that sigma of Sn is surjective. And in such a case, if this is surjective, then the V minus sigma of Sn, which is the boundary, will be exactly equal to Rn plus 1 minus Sn. And this set has two components. One bounded and one unbounded. Which means bounded, put it like this, U1, and unbounded U0, and of course U1, which is equal exactly to this particular value. So in such a case, we can assume, so we can also take P1 is equal to 0, and by the composition formula, we obtain that degree of tau composed with sigma is equal degree of f tau composed with f sigma, and this one is equal b1 0, and this one is equal to the degree. There is only one component, so there is no summation. So this is f tau, and p1 is 0, so this will be b1 0 times the degree of f sigma, and this is b1 0, and then implies that this is the degree of tau times the degree of sigma. And the statement follows. So the statement follows. So basically, that concludes my remarks about the Brouwer degree and local Brouwer degree and its properties. Of course, it would be appropriate to do some additional problems showing how useful, even from the point of view of the finite dimensional version of the degree, that is Brouwer degree, just in the topology of from the point of view of the topology of the Euclidean space, it is kind of important. So let me put it like this. Additional and I put here practice problem. And if you, of course, this is basically for those who follow the course to do this problem as a kind of exercise. If you have trouble solving these problems, so there are always several ways of dealing with it. One of them is basically look for a solution on the internet, in the resources. I'm pretty sure that all these statements can be easily identified in many kinds of the problems that other people are using. So in certain way you can prove it using the ideas that comes from someone else. But I believe that with the material that I have provided you, there shouldn't be difficulty in solving that. So problem number one. Problem number one is just simply let's say like this, prove the Brouwer fixed point theorem. Use the local degree to prove the so-called Brouwer fixed point theorem. Maybe let me write it down in different color, and this will be like this. Every map F from B, every continuous map, maybe it should be written continuous map F from B to B, where B denotes the closed map, a closed ball in V equals Rn, has a fixed point. So that's the statement. That's the problem one. Supposed to be very, very easy. So problem number two. Maybe like this. Show that every real n times n matrix, n larger or equal to 1, with all entries being positive numbers, has a positive eigenvalue. Has a positive eigenvalue. Okay, so let's go to the problem number 3. Suppose U in complex numbers is an open set, so this is C, complex numbers, so maybe make it clear, C, complex numbers, maybe is an open bounded set, and f that goes from U closure, we discussed that in such a case you can always think about the extension of U to be just to fit the definition, which means the degree is applicable to such situation with no problem. And f is a continuous U admissible map such that f restricted to U open is analytic. Show that degree of f of U is equal to number of zeros of f in U, so this is exact number of zeros counted with multiplicity. Counted with multiplicity. So, one more. Problem number 4. Proof the following. Borsuk-Ulam theorem. For every continuous map f from, let's say, Sn to Rn, so here n as usual larger or equal to 1, there exists x belonging to Sn such that f of x is equal to f of minus x. So that's the problem number 4. Problem number 5. Given a real number lambda larger than 0, show that the equation lambda minus z plus e to the minus z equals to 0 has exactly one solution. In the half plane, and this will be z belongs to c, and this is the real part of z is positive, real type of positive. And maybe two additional problems. Problem 6, suppose we have two functions f and maybe put it like this: sigma tau be two maps from Sn to n is of course larger or equal to 1. This is even dimensional sphere, our continuous map. Maps show that at least one of the maps sigma tau or sigma composed with tau has a fixed point. And finally, the last one. Show that Rn is not homeomorphic to Rn for n different in n. So that's it for today. Thank you. See you next time.